Close your eyes, take a deep breath, and let your mind wander through the mysteries of the universe. Look up on a clear night, and you will see thousands of luminous points piercing the darkness. But what are these lights that have fascinated us for millennia? Stars are, in fact, large spheres of extremely hot plasma, gigantic cosmic furnaces floating in the void of space. Each one tells a story of birth, life, and death that spans billions of years. These celestial wonders don't appear out of nowhere. They are born in stellar nurseries known as nebulae, giant clouds of gas and dust that float through the cosmos like ethereal veils. There, under the pressure of gravity, matter begins to concentrate, heating up more and more until something extraordinary happens. A star awakens. And what is a star, if not a natural nuclear reactor? At the heart of each one, unimaginable pressures and temperatures force hydrogen atoms to fuse, transforming into helium. It is from this process, this violent and beautiful atomic dance, that the brilliance comes that travels light years through empty space to reach our eyes here on Earth. But like all things in nature, this fuel is not infinite. When the hydrogen runs out, the star begins its final journey, its slow path towards cosmic silence. It is then that the star begins to die, although this death may take millions or even trillions of years to complete. Our own sun, that golden disk that warms us every morning, is just an ordinary, average-sized star. Nothing special in the grand scheme of the universe, just one among hundreds of billions in our galaxy. And yet, it is everything to us. But out there, in the vast ocean of space, there are stars thousands of times larger than the sun. Giants so immense that they defy our capacity for comprehension. The largest star ever recorded by astronomers may be about 700 times larger than our sun. Imagine, if we placed this giant at the center of our solar system, its surface would extend beyond the orbit of Saturn. It's almost impossible to imagine something so vast, so imposing. But here is one of the most fascinating paradoxes of the cosmos. Small stars live longer, while giant stars, in all their blazing glory, live only a few million years. It's as if the universe is saying that those who shine too brightly consume their essence too quickly. Some small and modest stars can live trillions of years, patient witnesses to the evolution of the universe itself. The color of a star tells us its temperature and its fate. Blue stars are the hottest and brightest, burning their fuel with fierce intensity. Red stars, on the other hand, are cooler, although cool is a relative term when we talk about objects that can still reach thousands of degrees. But these reddish stars have an advantage. They can live much, much longer. And there's something even more impressive. Some of these cosmic spheres can rotate thousands of times per second. Imagine all that mass, larger than the entire Earth, spinning faster than an airplane engine. It's a cosmic dance of incomprehensible speed and force. When a giant star finally exhausts all its fuel, it doesn't say goodbye quietly. It explodes in one of the most spectacular events in the universe, a supernova. For a few weeks, a single dying star can shine more brightly than billions of stars combined, illuminating entire galaxies. And from these cataclysmic explosions comes something precious. Supernovas create heavy elements like gold and iron, scattering them throughout the cosmos. The gold in your ring, the iron in your blood. All of this was born in the heart of a star that died billions of years ago. We are, literally, stardust. But not all stars disappear completely. Some leave behind ultra-dense remnants called neutron stars, objects so compact they defy logic. A teaspoon of matter from a neutron star would weigh billions of tons. It's as if the entire mass of a mountain were compressed into the space of a tiny rock. Some of these neutron stars become pulsars, rapidly spinning cosmic beacons emitting regular pulses of energy like the beating of a cosmic heart. When astronomers first discovered them, the pulses were so regular that some even considered the possibility that they were signals from alien civilizations. And what about our cosmic neighbors? The closest star to Earth, besides the Sun, is Proxima Centauri, a small red star hidden in the constellation Centaurus. Even so, being our closest neighbor, it is more than 4 light-years away. This means that the light we see from it today left there more than 4 years ago, traveling through the void of space at 300,000 kilometers per second. The space between the stars is vast beyond imagination, an ocean of silence and darkness punctuated only by these bright beacons. And while you rest comfortably under the sheltering roof, out there, above the clouds and the atmosphere, the universe continues its eternal dance. Stars being born, stars dying, stars spinning and shining through the ages, telling stories that began long before we existed and will continue long after we are gone. But not all stars shine the same way. This brightness, this luminous intensity that reaches us through the void, has a specific name: luminosity. And luminosity tells us a lot about a star. The larger it is, the more energy that star releases every second, pouring light and heat into the cosmos like an inexhaustible source of power. Some stars shine with such absurd intensity that they surpass the sun by millions of times. Imagine, while our sun is already bright enough to illuminate and heat an entire planetary system, there are stars out there whose light could do the same for thousands of systems at the same time. They are cosmic beacons of unimaginable power. However, the universe also has its shy stars, those that are barely noticeable. There are stars so faint, so discreet in their brightness, that even if you were relatively close to them, they would remain invisible to your eyes. Sensitive instruments would be needed just to detect their silent existence in the dark. And many stars don't live in solitude. In fact, solitude seems to be the exception, not the rule. Binary stars are fascinating systems where 2 stars orbit each other, locked in an eternal gravitational dance. They revolve around a common center of mass, sometimes so close that they seem to touch, other times separated by vast distances, but always united by gravity. And it doesn't stop there. There are even more complex systems, with 3, 4, or even more stars together, each following its intricate orbit in a cosmic ballet of multiple bodies. Imagine living on a planet orbiting such a system, where the sky could have 2, 3, or even 4 suns rising and setting in completely unpredictable patterns. Over time, stars don't remain exactly the same. They can gradually lose mass through stellar winds, constant streams of charged particles that escape from their surfaces and spread through space. It's as if the star is constantly blowing a part of itself into the cosmos. These winds don't simply disappear, they can create large bubbles of gas in space, ghostly structures that expand for light years, glowing softly with the residual energy of the star that created them. They are the luminescent shells left behind by stars in their final stages of life. But in binary systems, something even more dramatic can happen. A star can literally suck matter from its companion, like a cosmic parasite draining the essence of its victim. The stolen matter forms a disk around the vampire star, heating up to extreme temperatures before being consumed. And when this happens under specific conditions, the result can be catastrophic. These parasitic stars can accumulate so much stolen material that they eventually explode in supernovae that are even more violent than normal, releasing such an immense amount of energy that their brightness can surpass that of an entire galaxy for several weeks. Not all stars maintain a constant brightness. Some are variable, changing their luminosity over time in predictable or chaotic ways. It's as if they are breathing, pulsating with life. Some vary their brightness in a matter of seconds, in a quick cosmic blink. Others take years, decades, or even centuries to complete a cycle, changing so slowly that entire generations of astronomers need to work together to map their patterns. And then there are the baby stars, those that are still taking their first cosmic steps. T Tauri stars are these rebellious young stars, still forming, surrounded by disks of dust and gas from which planets may eventually be born. They are chaotic, unpredictable, ejecting material in powerful jets while still learning to control nuclear fusion in their cores. To better understand this stellar diversity, astronomers created an elegant classification system. Stars are organized into spectral types with letters that seem random at first glance: O, B, A, F, G, K, and M. Each letter represents a different temperature, a different color, a different type of star. Our Sun, that constant presence in our lives, is a G-type star. Yellow, hot but not extremely so, stable and reliable. It's a middle ground star, neither too big nor too small, neither too hot nor too cold. Perfectly balanced to support life on planets around it. But there are far more extreme stars. Type O stars are true blue monsters, extremely hot, burning with a bluish-white fury that far surpasses anything we can imagine. They are rare, violent, and ephemeral, living only a few million years before exploding in spectacular supernovas. At the other end of the spectrum are M-type stars, red dwarfs. Small, cool, unassuming. But don't be fooled by their discrete nature. These are the most common stars in the universe, the true rulers of the stellar population. In fact, more than 70% of all stars in the Milky Way are red dwarfs. Think about that for a moment. When we look at the night sky, most of the stars we can see are bright giants simply because red dwarfs are too faint to be seen with the naked eye. But they are there, billions and billions of them, slowly burning, living for trillions of years, silent witnesses to the history of the cosmos. And when the end comes, not all stars go out with a bang. Some die silently without a supernova, simply cooling gradually until they become white dwarfs, cosmic embers that will continue to shine faintly for billions of years before finally dimming completely. Others, however, refuse to depart silently. They explode with such force, with so much energy released all at once, that for a few days or weeks they manage to illuminate entire galaxies. Their brightness can surpass that of 100 billion normal stars combined, a final cry of defiance against the inevitability of death. And so the cycle continues, infinite and eternal. Stars are born, living their complex and varied lives, and eventually dying in silent or spectacular ways, each contributing its part to the great tapestry of the cosmos. And when we talk about these spectacular explosions, it's difficult to overstate their magnitude. A supernova can shine brighter than its entire galaxy for days or weeks. Imagine a single dying star, temporarily surpassing the combined brightness of 100 billion other stars. It's one of the most impressive spectacles the universe has to offer, a final declaration of existence before the final silence. But the story doesn't end with the explosion. After this cataclysmic event, what remains of the star can follow one of two extreme paths. If the mass is sufficient, but not too much, the core collapses into a neutron star, those incredibly dense objects we mentioned before. But if the mass is even greater, something even more mysterious happens. A black hole is born, a region of space where gravity is so intense that not even light can escape. And those colorful nebulae we see in spectacular astronomical photographs, those clouds of gas painted in vibrant reds, blues, and greens, they are remnants of dead stars, the veils left over after a star ejects its outer layers into the cosmos. They are beautiful cosmic tombstones, luminous monuments to the life that once existed there. There is something profoundly poetic in all of this, something that connects you, lying comfortably now with the stars out there. The iron in your blood, that essential element that allows oxygen to be transported to every cell in your body, was formed inside a star billions of years ago. In fact, every atom in your body, every particle that makes up who you are, came from the core of an ancient star that lived, shone, and died long before Earth even existed. Therefore, when they say we are made of stardust, it's not just a romantic metaphor. It's literally true. The carbon in your cells, the calcium in your bones, the nitrogen in your DNA, all of it was forged in the heart of stars that exploded ages ago. You are, in essence, the universe contemplating itself. Stellar matter organized in such a complex way that it gained consciousness. But let's turn our gaze to the night sky once more. Among all the stars visible from Earth, there is one that stands out above the others. The star Sirius, the brightest seen from our planet, shines with an intense blue-white in the constellation Canis Major. The ancients revered it, marking their calendars by it, and even today it captures our attention when it appears in the winter sky. And what about our own sun, that familiar star? It's about 4,600,000,000 years old and is roughly halfway through its life. It's a middle-aged star, stable and reliable, exactly the kind of star you'd want if you depended on it for survival. But nothing lasts forever. In about 5 billion years, when the hydrogen in the sun's core finally runs out, something dramatic will happen. It will begin to expand, gradually swelling until it becomes a red giant. Its surface will become cooler, acquiring a reddish hue, but its size will be immense. As it expands in this way, the sun could very well engulf Mercury and Venus, and perhaps even Earth. Our planet, if it still exists, could be consumed by the star that has nourished it for billions of years. It's a disturbing idea, but also comforting in a way. This will only happen in a future so distant that humanity, as we know it today, will have already evolved into something completely different, or spread among the stars, or disappeared long ago. After this red giant phase, the sun doesn't have enough mass to explode in a supernova. Instead, it will gently eject its outer layers, creating its own beautiful and colorful planetary nebula, and the remaining core will become a white dwarf. Small, approximately the size of Earth, but incredibly dense, still retaining a mass similar to what the sun has today. These white dwarfs are fascinating objects, cosmic crystals that glow with the residual heat they still carry. But without nuclear fusion occurring, they simply radiate this heat slowly into space, gradually cooling over trillions of years. And eventually, in a future so distant it's hard to even imagine, these white dwarfs will cool completely and become black dwarfs, cold, dark, invisible objects floating silently through the cosmos. But here's something interesting. No black dwarfs exist yet in the entire universe. The cosmos simply isn't old enough for any white dwarf to have had time to cool completely. The universe is only about 13,800,000,000 years old, and the cooling process takes much, much longer than that. Sometimes, a star may appear to twinkle or change in brightness, not because of internal processes, but simply because interstellar dust passes in front of it, like a cloud passing in front of the sun on a partially cloudy day. These small variations in brightness help astronomers learn more about the interstellar medium, that space between the stars, which is not actually completely empty. And many of those stars we see shining alone in the night sky aren't really alone. Some have planets orbiting them, distant worlds called exoplanets that orbit alien suns. Since the discovery of the first exoplanet in the 1990s, we've found thousands of them, each discovery expanding our understanding of the diversity of planetary systems that exist. Many of these stars may have entire systems similar to our solar system, with rocky planets nearby, gas giants further away, perhaps moons, asteroids, comets. Each of these systems is a unique cosmic experiment in planetary formation, and each may tell a different story about how planets are born and evolve. A star's personality changes with age. Young stars are more active and tempestuous, like cosmic teenagers full of uncontrolled energy. They emit powerful stellar winds, have enormous spots on their surfaces, and can release sudden bursts of radiation. It's a turbulent youth, full of drama and intensity. But old stars bring their own dangers. In their final stages, they can become unstable, releasing gigantic bursts of energy unpredictably. It's as if they are fighting against the inevitable, refusing to age gracefully. And some stars, particularly the massive and hot ones, emit radiation so strong and constant that it would make life impossible nearby. Their immediate environment is bathed in ultraviolet and X-rays so intense that any planetary atmosphere would be stripped away, any organic molecule destroyed. They are hostile environments, beautiful from afar but deadly up close. And so, each star has its own story, its own personality, its own destiny. From the small and modest red dwarfs that will live for trillions of years, to the blue supergiants that burn brilliantly for only a few million years, before exploding gloriously. And here, we find one of the most fascinating paradoxes of the cosmos. Massive stars, those impressive giants that dominate their cosmic neighborhoods, consume their nuclear fuel with incredible veracity. They live short, intense lives, burning through their hydrogen so rapidly that they last only a few million years. In cosmic time, that's less than a blink of an eye. On the other hand, small stars, those modest and discreet red dwarfs, are the true marathons of the universe. With their slow and efficient burning, they can live not for billions, but for trillions of years. In fact, no red dwarf that has been born since the beginning of the universe has even had time to reach middle age. They are all still in their stellar infancy, and will continue to shine long after larger and more impressive stars have disappeared ages ago. But if you think normal giants are impressive, prepare to meet the true queens of the cosmos, the hypergiants. These extremely rare stars are so colossal that they defy our comprehension. They are objects of such absurd power and size that they seem impossible, and yet there they are, existing in the far reaches of the galaxy. A blue hypergiant can have up to 100 times the mass of our Sun. Imagine compressing 100 suns into a single flaming sphere. These stars are so luminous that if one of them were in the place of our Sun, its radiation would instantly vaporize the Earth. They are cosmic furnaces operating at the absolute limit of what physics allows. And there is one of these titans that astronomers observe with a mixture of fascination and apprehension. The star Eta Carinae, located in the constellation Carina. This unstable and temperamental hypergiant could explode at any moment as a giant supernova. At any moment, in astronomical terms, could mean tomorrow or in 100,000 years, but it is definitely in its final stages. When it explodes, it will be one of the brightest astronomical events ever witnessed by humanity. And it's not the only famous star nearing its end. Betelgeuse, that red supergiant that marks the shoulder of the Orion constellation, is also approaching its cosmic demise. It has already begun to behave erratically, varying its brightness in ways that leave astronomers intrigued. It could explode in 1,000 years. It could explode tomorrow. Nobody knows for sure, but when it happens, it will be a spectacle visible even during the day, a second moon shining in the sky for weeks. But there's something unsettling about looking at the stars. Some of them are so distant that their light takes millions, even billions of years to reach us. When you look at these distant stars, you're literally looking into the past, seeing them as they were millions of years ago. This signifies something profound and somewhat melancholic. Many of the stars you see shining in the night sky may already be dead. They may have exploded, collapsed, or simply gone out long ago, but their light is still traveling through space toward us. They are luminous ghosts, messages from a distant cosmic past still in transit. When we talk about these cosmic distances, it's important to understand what a light year really means. Many people hear the term and think it has something to do with time, but in fact, light years measure distance, not time. A light year is simply the distance that light travels in 1 year, traveling at 300,000 kilometers per second. That's approximately 9.5 trillion kilometers. And many stars are thousands, millions, or even billions of light years away. Consider the journey that starlight takes. A particle of light leaves the surface of a distant star and begins to travel through the void of space. It can traverse billions and billions of kilometers, passing through clouds of interstellar gas, being deflected by the gravity of massive objects, traveling through the black void for eons, until it finally reaches a telescope here on Earth, or perhaps your own eye on a clear night. It's an epic journey that each photon of light completes. Stars are not normally born alone. They tend to be born in groups called clusters, stellar nurseries where dozens, hundreds, or even thousands of stars are born at approximately the same time from the same giant cloud of gas and dust. These clusters are like cosmic families, sister stars that share the same origin. Within a single cluster, you can find an impressive diversity. Stars of different masses, different colors, different destinies, all born together but each following its own evolutionary path. the most massive will die quickly while the smaller ones are still in their infancy. It's a perfect demonstration of how a star's initial size completely determines its fate. And when we look at our own galaxy, the Milky Way, the numbers become almost incomprehensible. We estimate that it contains more than 200 billion stars. 200 billion. It's such a large number that it's difficult to even conceptualize. If you tried to count one star per second, it would take you more than 6,000 years to count them all. And some astronomers believe that number could be even higher. There may be trillions of stars in the Milky Way when we include all the small red dwarfs that are difficult to detect, all the stars hidden in dusty regions, all those that simply don't shine brightly enough to be easily observed. Each of these stars is a sun, potentially with its own planets, its own stories. But stars are not just sources of light and heat. Some of them can be extraordinarily dangerous. Certain stars can emit bursts of gamma radiation, a type of extremely energetic and dangerous electromagnetic radiation. These bursts are so powerful that they represent some of the most energetic events in the universe. A well-directed gamma ray burst could literally destroy the atmosphere of an entire planet. The radiation would be so intense that molecules in the atmosphere would be destroyed. The ozone layer would be obliterated, and any life on the surface would be exposed to lethal levels of cosmic radiation. It would be an instantaneous and complete mass extinction event. If a gamma ray burst were aimed directly at Earth, it would be absolutely devastating. Scientists speculate that this may have caused mass extinctions in Earth's distant past, although it's difficult to prove. The good news is that these bursts are extremely focused, like cosmic lighthouses, so they would only be dangerous if aimed directly at us. And here's a reassuring fact. However, we don't know of any star close enough and in the right orientation to pose this threat. The most likely candidates to explode as supernovae and possibly release gamma rays are at safe distances and are not pointed in our direction. We can sleep soundly knowing that this cosmic danger, while real, is not an immediate threat to us. And there's another fascinating fact that challenges our perception of an unchanging sky. The stars move through space. All of them. Our own sun is traveling through the galaxy at more than 220 kilometers per second. Every second, our entire solar system moves more than 200 kilometers relative to the galactic center. It's an impressive speed, faster than anything we've ever built. Even so, when we look at the night sky, the stars appear completely still, fixed in their positions as they always have been. Why? Simply because the distances involved are so absurdly large that even traveling at hundreds of kilometers per second, it would take tens of thousands of years for there to be any perceptible change in the constellations. It's like observing the mountains on the other side of a vast valley, moving millimeters per hour. You simply don't perceive the movement. The stars are in constant motion, dancing through the galaxy in complex orbits around the galactic center, sometimes getting closer to each other, sometimes moving away. The sky we see today is different from the sky the dinosaurs saw, and it will be different from the sky our distant descendants will see. It's just another reminder that even the things that seem most permanent and unchanging are, in fact, constantly transforming. And speaking of galactic motion, our own sun has its own cosmic journey. It orbits the center of the Milky Way, completing a full revolution every 225 million years. Think about that for a moment. A galactic year lasts 225 million Earth years. It's such a vast period of time that our minds can barely process it. But here's something truly fascinating. This means that since life arose on Earth, approximately 3,800,000,000 years ago, our planet has already completed more than 20 full orbits around the galaxy. The first microscopic life forms on Earth saw the galaxy from completely different angles 20 times. Dinosaurs lived for almost an entire galactic orbit. The entire history of humanity, from the first stone tools to the rockets we send into space, has taken place in less than 1,000th of a single galactic orbit. And during these orbits, cosmic encounters can happen. Stars can get close to each other, and when this occurs, their immense gravitational forces can cause them to exchange matter. It's like a cosmic dance where the partners occasionally steal pieces from each other, redistributing mass through complex and beautiful gravitational interactions. And there is an even more dramatic event in our cosmic future. In approximately 4.5 billion years, our neighboring galaxy, Andromeda, will collide with the Milky Way. When we say collide, this may conjure images of catastrophic destruction, of stars crashing into each other in apocalyptic explosions. But the reality is very different, and in some ways even stranger. The stars probably won't collide directly. Why? Because the space between them is absolutely enormous. Even within a densely populated galaxy, the stars are so far apart that the probability of two of them actually colliding is astronomically small. It's like taking two swarms of bees, each with billions of bees, and making them pass through each other. The individual bees probably wouldn't touch. Instead, something more majestic will happen. The two galaxies will slowly merge, their stars being rearranged by gravity into new patterns, new spiral arms, new structures. Eventually, they will form a new giant galaxy, a merger of both, which astronomers have already affectionately nicknamed Milkomeda or Lactomeda. It will be a massive elliptical galaxy, very different from the spirals that formed it. But not all stars follow tranquil orbits. There are stars that orbit dangerously close to supermassive black holes, those gravitational monsters that reside at the centers of galaxies. These stars dance on the edge of the abyss, moving at incredible speeds, constantly on the verge of being torn apart by extreme tidal forces, yet somehow remaining whole. Some of these central stars travel at speeds that defy imagination. The fastest ever recorded move at over 24 million kilometers per hour. To put that into perspective, at that speed you could travel from Earth to the Moon in about a minute. It's such an absurd speed that it begins to approach a significant fraction of the speed of light. And sometimes, in these close encounters with black holes, something extraordinary happens. A star can receive such a violent gravitational pull that it is literally ejected from its galaxy, hurled into intergalactic space like a stone from a cosmic sling. These exiled stars are called hypervelocity stars, solitary travelers condemned to wander forever. A hypervelocity star can wander eternally through intergalactic space, that immense void between galaxies where practically nothing exists. It will never again feel the gravitational embrace of a parent galaxy, never again have nearby companion stars. It is condemned to absolute cosmic solitude, traveling through the black void for billions of years, a solitary witness to the vastness of the universe. But not all stars are so dramatic. Some have their own calmer rhythms, their own steady beats. Pulsating stars expand and contract regularly, changing brightness predictably, It's as if they have a giant beating heart, a cosmic pulse that can be measured and studied. Some pulse every few days, others every few hours, keeping time with a regularity that sometimes surpasses our best atomic clocks. And the light from these stars, this radiation that travels through the cosmos to us, carries precious information. Starlight can reveal the exact chemical composition of a star, even if it is thousands of light years away. How? Through an elegant process called spectroscopy. When the light from a star passes through a prism or diffraction grating, it splits into a rainbow of colors. But this rainbow is not continuous. It is cut by dark lines at specific wavelengths, called absorption lines. Each chemical element absorbs light at unique wavelengths, leaving its characteristic signature in the spectrum. By analyzing these lines, astronomers can accurately identify which elements exist in a star's atmosphere and in what proportions. It's like reading a star's chemical recipe from its light. And when a massive star finally reaches the end of its life and explodes in a supernova, it doesn't just disappear. It scatters new matter throughout the universe, all those heavy elements that were forged in its core during billions of years of nuclear fusion. Carbon, oxygen, silicon, iron, gold, uranium. All these elements are launched into interstellar space in a violent explosion. And here's the truly profound part. Without the death of stars, planets like Earth would never have existed. The first generation of stars in the universe contained only hydrogen and helium, the elements created in the Big Bang. All elements heavier than that, everything necessary to make rocky planets, oceans, and eventually life, had to be created inside stars and then scattered throughout the cosmos when those stars died. You are made from the remnants of dead stars. Your planet is made from the remnants of dead stars. Everything you see around you, except the hydrogen in the water you drink, was forged in the heart of an ancient star. Death is necessary for life. It is a cosmic cycle of birth, death, and rebirth that has repeated itself for billions of years. Every star in the sky carries the history of billions of years in its light. Some are young, newly born from clouds of gas enriched by the death of previous generations of stars. Others are ancient, almost as old as the universe itself, silent witnesses to all of cosmic history. Each one has a story to tell, if only we knew how to listen. And the cycle continues. Some stars can collapse and be reborn in new forms, transforming from red giants into white dwarfs, or from supergiants into neutron stars, or into black holes that can eventually seed the formation of new stars around them through their gravitational influence. Matter is never destroyed, only transformed, reorganized, recycled through increasingly complex forms. And there's one last thought to contemplate as you relax. The universe may be full of stars we will never see. Stars so distant that their light hasn't yet had time to reach us. Stars hidden behind clouds of interstellar dust. Stars in other galaxies so remote that they are beyond the observable horizon of the universe. Each one exists, shines, lives its cosmic life, completely unknown to us. And as long as there are stars, there will be new stories to discover. Each astronomical observation reveals something new, something unexpected. We find stars that challenge our theories, that force us to rethink what we thought we knew. We find stars with bizarre properties that we can barely explain. And each discovery reminds us of how vast and mysterious the universe truly is. The stars will continue to be born, live, and die, long after humanity has disappeared. They will shine through unimaginable ages, silent witnesses to the passage of cosmic time. And perhaps, somewhere out there, around one of those countless stars, there is someone looking up too, contemplating the same questions, marveling at the same vastness. For now, as you prepare to sleep, know that you are part of this cosmic story. You are the universe experiencing itself, star matter organized in such a complex way that it has gained the ability to look back at the stars that created it and feel awe. It is a deep and beautiful connection that unites us with all that exists. And with that comforting thought, let your mind drift gently toward sleep, knowing that above you, beyond the clouds and the atmosphere, the cosmos continues its eternal dance. Stars rising, stars setting, stars shining through the endless night, each one a wonder, each one a mystery, each one part of the same cosmic tapestry of which you are also a part. Good night, cosmic traveler. May your dreams be as vast as the universe, and as bright as the stars that illuminate it.